You're going to do two tests on the transformer. They are so practical. You do it in industry, this practice. Two tests for or perform on transformer, single phase. The first test is called no load test or open circuit test. What we'll do in this test, and what's the objective of this test? The objective of this test is to determine the cool loss in the transformer and determine the value of the magnetizing reactance of the transformer. Two things that we need to find: cool loss and the magnetizing reactance responsible for the magnetization in the cool of the transformer. Well, condition: we got to apply the voltage by the same frequency. We cannot change the frequency. If the frequency of the transformer 60 Hz, we should apply 60 Hz, not 30, not 50, nothing else. Why? Because the frequency will affect the value of the reactance, will affect the value of some loss in the hysteresis. So we got to be sticking to the values of the rated values of the transformer. So that's number one. Where should we perform the test? Low voltage side test or high voltage side test? Either one correct, but there are recommendations. The recommendation that the voltage should be applied to the low voltage winding, and as you see here in this diagram, that's the low voltage side, and that's the high voltage side to the right. You open the circuit at the high voltage side and apply the voltage at the low voltage side and put all the measuring instrument on the side. Why prefer that? Because it's safe. It's better just to deal with the low voltage side, not to apply voltage like 1,000 volt or 2,000 volt in the high voltage. No, just leave it open and just put all your measuring instrument at the low voltage side to be safe, just only for safety reasons. Okay. You keep the secondary open, in this case, the high voltage side. So what's happening when you open the circuit? There is no load. Or you can say RL is equal to infinity, so the current is equal to 0. So actually, when you look at the current here in the high voltage side, it's 0. So what's happening here on the primary? Even if you remember, and this just goes with it, if you know I secondary is equal to 0, so IP will be equal to 0 because you say 0 over A is equal to 0. But you will measure current, you will measure voltage. And when you go to the lab, you find there is current value, there is voltage. What meter measuring? Power. How come? And the current is 0. Well, current is 0. Means that there is some kind of current the transformer take it, not because of the load. That's true. The transformer draws current, not to supply load, to supply other things. Supply the cool loss, the magnetization in the core, to build the magnetization, the magnet in the magnetic field inside the core. So how you can calculate these things and how can you represent it? Well, let's take just numerical values. That's a test we did it on transformer, 48 kilovolt amp transformer, 4800 240 volt. So we are going to make the open circuit test. The open circuit test here on this side, all right, and this side, and this side we are going to put the measuring. And then usually you will find a table. Open circuit test, voltage is 240, current is 2 amp, power is 120. What are these? These are the measurement of the wattmeter, voltmeter, ammeter, and that's exactly what we're going to do tomorrow in the lab. Okay, so how can you use this data for obtaining the circuit to the right? The objective is to find this branch that's representing the no load. All right. Well, I have systematic steps that will help you to find the open circuit equivalent circuit, as you see in the right. And by the way, when you do the measurement on the side, all right, obviously we did it on the low voltage side, true? That side, the 240 voltage. How do I know that? Because when he said the voltage, the measure it's 240. That's number one. Number two, when you do the test, when you perform the test, you should apply the rated value. So this is the rated value of the low voltage side. So that's the low voltage side, and that's the high voltage side. So I know this is the voltage. So I'll say you just write that the open circuit voltage is equal to 240 voltage, and the current open circuit is equal to amp, and the open circuit power is equal 120 watt. That's the first thing we do. That's the data that you are going to measure in the first thing you can do. You can find this resistance the first thing. What is the resistance RC1? That's the core loss resistance that represents the core loss. What is the value of the core loss? It's given here by the wattmeter measurement. It's 120 watt. So you can say the core loss in the transformer, which will be constant, whatever it's loaded or not loaded, that will be equal to the open circuit power 120 watt from the measure. That's the first thing. Core loss is just measured. And resistance RC. Well, as you know, any power is equal to what? V squared over R, right? That's a fundamental relation that you got it in circuit 1 and 2. So if you want to find the resistance, how you find the resistance? You divide the square value of the voltage by the power. True? So now I can find the core loss resistance, and I'll say RC1 or RCL if you wish. RC, it means core loss resistance, L is side. So that will be equal to the voltage open circuit divided by the power open circuit, or the core loss is like the open circuit voltage is given 240 voltage square divided by the power of open circuit, which is equal to 120, and you get the resistance, which is equal 480 ohm. So that will be the resistance that represents the core loss. You got the first one. That's exactly what you will do in the lab, in the calculation and simulation. Let me just see what we're supposed to get. We're supposed to two parameters, RC and XM. We got RC. How can you find XM? That's XM. How we can find the value of the reactance, magnetizing reactance. From the information of data that you got. We have all data and you can build something. So how do you get XM? That's I1, and that will be the current open circuit. We agree that the current, this is coming from, if you wish to complete the circuit, that's the second day, and we said the current here is equal 0, and here will be 0. So the all open circuit going I1, because the other side is 0. Why 0? Because I2 is equal 0, open circuit. So IB equals 0. So the all current you are measuring, there is nothing next to this winding, it's 0. So IOC is exciting current, excitation current. That's going like that, and this then get IC1. How we get IC1? IC1, you divide the voltage, the current, and the resistance. You can do it by dividing the voltage by the resistance. Just calculate. The voltage is equal to 240 voltage, and the resistance, we just got it here, 480. What is the value of this one? 0.5 amp, right? So the current IC1 is equal 0.5 amp. If you know that the current here, IOC or open circuit current, you know, it's equal to amp, and here will be 2 amp. and you got the resistance. So can you get the IC? We got yes, IC1. What about the current in the XM1? Oh, you get it. Let's just show you some. If you have, let's say, just we'll have, let's say that you know the value. Just I'll remind you by something in circuits. Let's say that you have 100 voltage and you have 10 ohm and you have J5 ohm. Let's say that you're knowing that. So what happened the current here? Call this, for example, IC, call this one IM, call this one I5. Let's say that, assume that you know. So IC will be equal to 100 over 10 will be equal to 10. Remember, we assume this on angle 0. IM will be equal 100 divided by J5, what you have, minus J20. So if you ask you what is the current, the total current I5, which is the same thing, open circuit, you will say it's equal IC plus IM. IC is equal 10 minus J20. What do you observe? The current has two components. One, if you sketch it, you got one is equal 10 and the other one negative 20. So it's perpendicular, right? They are orthogonal to each other. So putting that in my mind, so I know it's something like that in x-axis and something on the negative y-axis, perpendicular. All right. If I ask you to find the magnitude, what you will do? You will say the magnitude of the open circuit will be equal to IC square magnitude plus IM magnitude square. You get the whole value of open circuit, right? All right. So we did that just to understand how we'll go back in the reverse direction. I'll go there. So our problem here. And I have IC1. I don't have IM1, but I know that I open circuit magnitude square is equal IC 1 IC 1 square plus I magnitude square. Now I know the open circuit is equal to 2 amp, the magnitude. And IC1, I just got it, 0.5 square plus IM1 magnitude square. So I will say the magnitude of the current in XM will be equal 2 square, which is equal to 4 minus 0.5 square root, and then I get the value for the current in XM. It's a very simple circuit problem. So root, I got one, I don't know if it's right or not, 1.94. Somebody check if I got the right. Okay, so that's IM. You know IM, you know the voltage you can get XM. Why? Because here you go. That's V and that's X. When you divide V by X magnitude, you get the magnitude of IM. So I will say IM is equal to voltage divided by XM. So how you find XM? So XM is equal to V open circuit divided by IM magnitude. The open circuit voltage is equal to 40 voltage divided by magnitude, which is equal to 1.94, and we get the value for XM, which is equal 123.94 ohm. That's RC and got XM. But you got RC and XM, which side? Low voltage side. The question asks you to find the core loss resistance and magnetizing reactance on the high voltage side. What you do? Use the rule. That's just read in the quiz. You say R2 over R1 is equal M2 over M1, and then check what do you have in 2 and 1, and the other one be dash, and then you do the same thing with it. So I'm not going to confuse you. Just I want to focus on how you find the resistance and the reactance in open circuit test, and that's how we do it. Do you have any question? But some can use different things. For example, you have the power, and you can get the apparent power by multiplying the voltage open circuit and the current open circuit. You get the apparent power, S. And then if you say you want to find Q, you have S, you have P, you get Q. Once you get Q, Q is related to X. Then you can get. There are other way. I'll put it in the folio, but I don't want to give you two methods now. Just I'm giving you the easiest one that you can do using circuit. So you got the R, you got the X, and they are in parallel. You always in parallel like that, and next to the voltage supply. So by this test, you got the cool loss resistance, you got the magnetizing reactance. Now, the second test. The second test, it's called short circuit test. And this short circuit test, we flip it. Also, you can do it anywhere. You can do it on either side. You could do the test on low voltage side or high voltage side. But in this case, as you see here in this diagram, we make short circuit on the low voltage side. Like this, if you look at this, that's the low voltage side. And the high voltage side, where you put the voltage supply and the measuring instrument. But this test is really important because it can cause harm to the transformer if it's not performed right. And so I want to mention it here before you go, and then blue fuses. I want to see this test. Open circuit is safe because there is no load. It's just, and the no load current is really small. But this one, you're going to short circuit. It means that the resistance is equal to 0. The current will be maximum. So do you expect when you put the voltage source on the high voltage side, you're going to use the rated value of the voltage? That's a question, common sense. You short circuit the secondary, and you have the all measuring instruments and the power supply at the high voltage side. Are you going to apply the rated voltage of the transformer? No. Why? At any side, the other side, you should put the rated load, you get the rated current. Like let's say that the transformer in the lab, the rated current is 5 amp. So if you apply the rated voltage, reasonable resistance, it will draw the 5 amp. But if you make it short circuit, so the current will go to infinity. So the voltage divided by 0 is equal to infinity. If you put just some resistance of the wires, 1, 2 ohm, still high. It blew the fuse. So what you'll do, you put the voltage on 0 on the high voltage side and gradually increase it. And on the simulation, because you will do the same thing when you do the hardware, and keep your eye on the current. And once you reach the rated current, okay, so you don't put the rated voltage, but you increase the voltage gradually, and you have to wait because the response takes time. And you will find in the simulation and the hardware if the current is getting really bright greener than the normal situation. So what you're supposed to do, just gradually increase the voltage applied till you get the rated value at both sides. Okay, so what you're going to get from this test, you're going to get the equivalent resistance, equivalent reactance of the whole transformer. Refer to the side where you put your measuring instrument. Let's just have a numerical example. The same transformer that we operate on the open circuit test, you're going to do the short circuit test. We do the short circuit test on the low voltage. It means that 240 will be shorted, and 4800 volts will you put the and you look at this arrow, it means you are changing the voltage on the input. And what's happened? You got 10 amp. Where you got the 10 amp here on this side? You got 10 amp. And the voltage was 150 voltage only. Remember, that was at the high voltage, which should be 4800 volts. Just you stop at 150 because you get the 10 amp. All right, that's even. Okay, what happened now? The power measurement is 600. So what you will get? But first, you should ask what you expected from this test to get. Well, expected if you are having the all measuring instrument on the high voltage side, so you are getting the equivalent impedance on high voltage side. So that's high voltage side. So you have R equivalent H, X equivalent H. You're getting the equivalent impedance on the high voltage side. That's why I write H. E equivalent. So the measurement here. So how can you find the resistance and the reactance? Somebody give me any suggestion about it. Always the easy thing to get the resistance. How you get the resistance? RE1, REH. Find the resistance REH. The voltage current power. What you get? So if you divide the voltage by the current, what you get? Across the resistance? Source and the rest of the circuit, right? So it's measuring the voltage across what? The whole transformer. So it's the voltage across what? Impedance, right? Magnitude, right? So if you divide the voltage of the short circuit by the current of short circuit, you'll get the impedance, the equivalent magnitude, because we're not talking about angle yet. All right, because you got to know that's the resistance, and that's the inductance, and that's the impedance. So you have R equivalent H, you have X equivalent H, you got. So if you divide the voltage by the current, you get the whole impedance on the other side, because that's the voltage that you put the, and that's the amp. So that's the amp, that voltage from here, it's up to here. All right. And by the way, this is short circuit. So the voltage across these 2 points is the same across this impedance. With short circuit inside. Now, if you divide, you will have 150 divided by 10, you get 15 amp. What about the resistance? Resistance is related to the power loss. The power is equal to 600. So we'll say that the power is equal to what? Is equal I squared times R, because the current here going in the, if you go there, that's I. So you'll say R equivalent H is equal to power divided by I. The power is equal to 600 and the current is equal to 10 amp square. So what you'll get? 6 ohm. You got the resistance equal 6 ohm. You got Z is equal 15. Go here, 15 and 6 ohm. Can you get X? Yes. Oh yeah, you're right. Thank you. You got Z, you got R. Can you get X? Yes, you can. How you get X? Pythagoras. Z equivalent. Square root. So you got 15 squared minus 6 squared square root. You get the value for X. So you got 15 minus 36 square root. You got 13.7 ohm. That's it. So your impedance of the whole transformer is equal to 6 plus J 13.7. You got that? you can get anything. Why? Because now the equivalent circuit, here you go. That's what we got. That's the RC, that's the XM, or refer to the some side. And that's the resistance, and that's the inductance, and that's it. But you have to refer to this one I did to the high voltage side. So what I did, I made transformation for R and X to the high voltage side because it was measured at low voltage side by using A squared. And that's what we got, was already in high voltage side. I didn't have to do any transformation, 6 and 13.75. Because if you remember, the value for the open circuit test that we got, these are the value. RL for 80 and XM 123.94. So I did transformation because that was a low voltage side. So you cannot put two parameters from different references for high voltage side. I did everything in high voltage side. So in the end, you got the circuit. And with this, you can solve transformer easy. If you want to put load, you can put the load, you can put the voltage source, and you can calculate everything using one circuit, not two sides as we did last practice, E1 and E2 transfer. No, just one circuit.